Hey there, and welcome to today's Explainer. I am absolutely thrilled to have you here as we dive into the fundamental physics that literally govern our universe. Today, we're unlocking the secrets of Chapter 33, Electromagnetic Waves. We're going to look at the invisible structures that allow us to see, communicate, and frankly, to exist.
Okay, let's dive into this. Here is our system diagnostic menu for today. We'll be hitting 1. Maxwell's rainbow. 2. Anatomy of an EM wave. 3. The Poynting vector. 4. The push of light. And 5. Filtering with polarization.
Look at that number, 299,792,458 meters per second. That's the constant C. It's the absolute, unbreakable, universal speed limit for all electromagnetic waves in a vacuum. It really doesn't matter what kind of wave we're talking about. Out in the vacuum of space, they all obey this exact speed limit. No exceptions.
All right, starting with Section 1, Maxwell's rainbow, scanning the spectrum.
You know, when we talk about light, we're usually just thinking about visible light, right? The colors we can actually see. But actually, that's just an incredibly tiny sliver of a much, much broader spectrum. The full electromagnetic spectrum contains a vast array of components. We're talking radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. These ranges do totally different things for us in the modern world, everything from broadcasting your favorite TV channels to advanced cancer therapy. But here's the wild part. They all share the exact same basic nature, and they travel at that exact same speed, c. The only thing that differentiates a radio wave from, say, an X-ray is its frequency and its wavelength.
Moving right along to Section 2, Anatomy of an EM wave, a holographic breakdown.
So, what do these waves actually look like? Imagine if we could just freeze time for a second. On the left side, we've got the electric field, or E, and it's oscillating up and down on the y-axis. Over on the right, we have the magnetic field, or B, oscillating side to side on the z-axis. Notice how both fields are perfectly perpendicular to each other? And, crucially, they're both perpendicular to the x-axis, which is the direction the wave is actually traveling. It's kind of like thorns on a rose stem, you know? The field vectors point away from the axis of travel. This right here is exactly what physicists mean when they say a transverse wave.
There's a great quote describing this: "A most curious wave. It requires no medium for its travel." Just pause and let the profound weirdness of that sink in. The mechanical waves we're used to every day, like sound waves traveling through the air or ocean waves crashing at the beach, they absolutely require a physical material to move through. But an electromagnetic wave? It doesn't. It can travel perfectly through the dead vacuum of deep space. Which should instantly spark a question in your mind. How on earth does light travel through absolutely nothing? I mean, if there's no water to ripple and no air to compress, what exactly is waving? Well, this brilliantly illustrates one of the most elegant mechanisms in literally all of physics, the infinite feedback loop. Here's how it works. Step 1. Faraday's law dictates that a changing magnetic field induces a perpendicular changing electric field. Step 2. Maxwell's law comes in and says that this newly changing electric field induces its own perpendicular changing magnetic field, and so on, forever. The two fields continuously create each other via induction. They basically pull each other forward by their own bootstraps, propelling the wave endlessly through the vacuum. How cool is that?
Let's move to Section 3, the Poynting vector, calculating energy transport.
Now, these self-sustaining waves aren't just mathematical curiosities. They carry real, measurable energy. Enter the Poynting vector, which we denote with the letter S. This represents the rate of energy transport per unit area. We find it by taking the cross product of the electric and magnetic fields. The magnitude of this vector gives us the instantaneous rate of energy flow, which we measure in watts per square meter. Meanwhile, the direction of the vector tells us exactly where the wave, and therefore the energy, is heading. So, by observing these oscillating fields, we can calculate exactly how much energy is hitting a target at any given instant.
Next up, Section 4, the push of light, radiation pressure.
This brings us to a seriously mind-bending physical reality. Light doesn't just transport energy to warm us up, it actually carries linear momentum. It can physically push objects. We call this radiation pressure, which is the physical force per unit area exerted by electromagnetic waves when they strike a target. Now, when a camera flash goes off in your face, you don't feel a physical punch, right? That's because the pressure from that brief flash is way too small for human nerves to detect. But it is there. And when we use highly focused lasers, or factor in the vast amounts of sunlight constantly striking the Earth, that force becomes intensely real and measurable. To see exactly how this force works, let's look at the difference between two scenarios: total absorption versus total reflection. If a surface is completely black and absorbs all the light, the radiation pressure is simply the intensity of the light, I, divided by the speed of light, c. But check out the bottom row. If you bounce that light off a perfectly reflecting mirror, the force and the radiation pressure actually double, becoming 2I over c. Literally, the act of making a light wave reverses its direction, transfers twice as much momentum to the object.
Now, what's really interesting about this concept is how we can apply this intense math to something super thrilling: space travel. Because reflection doubles the radiation pressure, we could theoretically build a spaceship equipped with a massive, perfectly reflecting foil sail. Driven entirely by the continuous radiation pressure from the sun, this ship could be propelled completely across the solar system, and we wouldn't need to carry a single drop of conventional rocket fuel to do it.
Finally, Section 5, filtering with polarization, controlling the waves.
Let's look at one more way we can manipulate these powerful waves. On the left, we have unpolarized light. Here, the electric fields are oscillating randomly in all possible directions, perpendicular to the wave's travel. This chaotic mess of arrows, that's exactly what you get from common light sources like the sun or standard light bulb. But on the right, we have polarized light. Here, the electric fields oscillate cleanly in one single organized plane. TV broadcast signals work exactly like this. By passing unpolarized light through a polarizing sheet, which structurally acts kind of like a picket fence, we can filter out all those perpendicular components. This neatly aligns the wave and cuts its intensity exactly in half.
So, we've seen how these waves continuously recreate themselves in a vacuum. We've seen how they carry energy, how they can physically push massive objects, and how we can filter their geometry. Which leaves us with this final thought. If light can do all of this, if it can power data across the galaxy, and act as a limitless engine for spacecraft, what will we engineer it to do next? Thank you so much for joining me for today's explainer. I really hope you walk away with a profound new appreciation for the light filling the room around you.